Having understood the bioenergetic principles of electron flux through the respiratory chain, we can now look in the final details of how this electron flux is coupled to pumping of protons across the inner mitochondrial membrane by the respective components of electron transport chain. And for that we need to go back to the physical outfit of the respiratory chain. From the physical perspective, the components of the respiratory chain could be divided into ones representing large protein complexes embedded in the membrane, the standalone proteins, and small molecules. So the first class is represented by the complexes 1, 2, 3, and 4 embedded in the inner mitochondrial membrane. The second class is represented by standalone electron carrier protein cytochrome C, which is, as I mentioned earlier, soluble proteins, protein present in the mitochondrial lumen. And the final class, this small molecule components, is represented by ubiquinone. The proton pumping is in fact generated only by three largest protein complexes within the respiratory chain: complex 1, 3, and 4, while others mainly perform electron carrier function. Complex 1 represents the first entry point of electrons into the respiratory chain. It is also known as NADH dehydrogenase, as we discussed earlier, or known as NADH ubiquinone oxidase reductase. NADH dehydrogenase is the largest complex of the electron transport chain. It consists in our cells of approximately 50 different polypeptides and have mass of roughly 1 megadalton. It has overall L-shaped form with the membrane arm embedded in the inner mitochondrial membrane that harbors 4 proton pumping channels, and also has the stalk that projects into the inner mitochondrial into mitochondrial matrix. The catalytic site that catalyzes the dehydrogenation of NADH, oxidation of NADH, is located at the very tip of the stalk, and the binding site for ubiquinone, which is used to reduce ubiquinone to ubiquinol, is located at the junction between membrane arm and the stalk facing the lipid face of the inner mitochondrial membrane. The two protons and two electrons are initially accepted at the catalytic site and transferred to flavin mononucleotide, which is flower protein prosthetic group within complex 1. The two electrons are then transferred through the chain of iron sulfur clusters located within the subunits of the complex 1 within the stalk, and act as a akin to electric wiring that transfers electrons that finally are accepted by ubiquinone in the ubiquinone binding site along with two protons, and releasing the reduced form of ubiquinone into the lipid phase of inner mitochondrial membrane. So the electrons are moved through this wiring chain by the electromotive force generated due to different electron affinities, different reduction potentials between NADH and ubiquinone. So this transfer, this potential difference, releases free energy, and free energy is used to induce series of conformational changes within the stalk, which is transferred to membrane arm, and as such the series of conformational changes induces a cyclic change within the conformation of proton pumps within the arm, such that uh, 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 the channels are preferentially accepting protons in the mitochondrial matrix in the initial stage of the cycle and release the protons into outside the inner mitochondrial membrane at the later stage of the cycle. So the function of complex 1 pumping protons outside generates the charge distribution between the inner and outer mitochondrial membrane such that the matrix becomes partially negatively charged and therefore referred as to negative side, and the outside luminal space of the mitochondria becomes partly positive charged and therefore referred to positive side. So the function of complex 1 could be summarized by a balance equation similar to what is done in the case of chemical reactions, except that instead of transferring protons between chemical compound, we deal with transferring of protons between the negative side and positive side of the mitochondrial compartments, which are referred to as with subscript n and p respectively. So initially the complex 1 accepts one NADH, one oxidized form of ubiquinone, and in total 5 protons from the negative side of the membrane, and ends up by releasing the oxidized form of NAD+, the reduced form ubiquinone, and 4 protons which are released on the positive side of the mitochondrial membrane. The another entry point of electrons into respiratory chain is complex 2. Complex 2 is also known as succinate dehydrogenase, and as such it performs the dual function, being electron acceptor for the electron transport chain and the enzyme performing one of the stages of the runabout of chemical reactions within citric acid cycle, oxidizing succinate to fumarate. So the electrons donated during this oxidation step are transferred to FAD prosthetic group within succinate dehydrogenase along with 2 protons, and then electron transferred similar to the complex 1 through the chain of iron sulfur cluster wiring, and are finally used to reduce ubiquinone from oxidized to reduced form. Interestingly, unlike the complex 1, the transfer of electrons from through complex 2 does not result in the pumping of protons across the inner mitochondrial membrane, and the bioenergetic reasons of this is that the change in the reduction potentials between the FAD within complex 2 and ubiquinone is much smaller as compared to the respective difference between NADH and ubiquinone within complex 1, and because of that the free energy release of this transfer is much lower in complex 2 as compared to complex 1, and as a matter of fact it is not sufficient to pump any protons. So this step is therefore at this point the complex 2 functions only at the entry point of electrons into electron transport chain. The So the electrons harvested in the form of reduced form of ubiquinone from complex 1 and complex 2 travel with these reduced forms through the lipid phase of inner mitochondrial membrane and end up on complex 3 that contains a system of cytochromes that have high affinity of electrons, higher reduction potentials than ubiquinone. Uh, and as a net product, the complex 3 catalyzes or mediates the transfer of electrons from ubiquinones, reduced form ubiquinones, reducing them back to oxidized form, and channels this electron flux through the complex 3 to cytochrome C, which has even higher reduction potential, and this net change in the reduction potential between ubiquinone on one end and cytochrome C on the other end is used the electromotive force generated by this transfer is utilized to power the um, proton pumping from the negative side again to positive side, increasing even more the proton concentration along the two sides of mitochondrial membrane. The complex 3 is quite large multi-protein assembly, but could be sort of as a complex consisting of two halves, each approximately equal to one another, consisting of multiple subunits. So let's see how actually complex 1 the transfers the energy of electron flux, energy of electron motive force to pump the protons. So the two halves of the this large complex would essentially generate a cavity within the lipid phase of the inner mitochondrial membrane that could accept and release several ubiquinone instances at once, and could mediate complex channeling of electrons between these instances and the cytochrome C as a final electron acceptor. And its functions, the way it functions and pumps the protons, could be divided into two stages, which are referred to as ubiquinone cycle or Q cycle. So the cavity, bipartite cavity of the generated by cytochrome C has two acceptor sites for ubiquinone each half, and one half can accept the ubiquinone and another half can accept ubiquinone both on the positive and on negative side. The ubiquinone acceptor sites are coupled, electrically coupled by the hems of cytochrome B. This way generating an electric wiring that connects to ubiquinone acceptor sites. On the positive side, there is also the iron sulfur clusters that performs function of electric wiring that connects the ubiquinone acceptor sites, positive ubiquinone acceptor sites, with the cytochrome C binding slots which in the end used to transfer electrons and reduce cytochrome C. So in the beginning of the first stage, the one instance of fully reduced ubiquinone from complex 3, from complex 1 and 2 is accepted on the positive side, and simultaneously the fully oxidized form ubiquinone is accepted on the negative side. The fully reduced ubiquinone is subsequently oxidized completely and released to the lipid phase of the mitochondrial membrane. The two protons get channeled outside on the positive side, and the two electrons, one is wired through iron sulfur cluster and reduces one instance of cytochrome, and another one is channeled down to the ubiquinone sitting in the negative side and reduces it to semiquinone radical. And this the fact that the semiquinone radical is formed as an intermediate will be important later in our discussion on the connection between the electron transport chain function and the generation of free radicals, which are harmful for the cell. But at the end of the first stage of ubiquinone cycle, we end up with ubiquinone free radical, one reduction of the fully reduced ubiquinone to fully oxidized, and then transfer to protons, reduction of one cytochrome C, and this is the stage for the second stage of the Q cycle, where complex 3 accept yet another instance of fully reduced ubiquinone and on its positive side, which again undergoes the same kind of interconversion, donating fully oxidizing, releasing two protons on the positive side and two electrons, one which channeled through the iron sulfur cluster to reduce another instance of cytochrome C, and another one channeling down to finally reduce semiquinone radical to fully reduced ubiquinone, simultaneously picking up two protons from the negative side. So each of these stages could be sort of as a balanced into separate chemical reaction, similar to what we did for complex 1, and the outcome of the balance from the first stage and the second stage can be summarized together to give the final outcome of the Q cycle, the cycle of a complex 3 function where reduced form ubiquinone is oxidized, and during this is accompanied by a reduction of two instances of cytochrome C, shuttling them to a fully reduced state, and concomitantly transferring two protons from the negative side and releasing four protons on the positive side, where this balance between negative and positive is compensated by this two protons picked up from ubiquinone, which was floating within the inner mitochondrial membrane. So finally, the cytochrome C, which is a soluble protein, which is actually traveling, diffusing within the lumen between the inner mitochondrial membrane and outer mitochondrial membrane, is accepted on the final part of the respiratory chain complex 4. That's also a large transmembrane complex that works as a proton pump. The complex 4 contain systems of A-type cytochromes, and the copper iron centers consisting of copper clusters, and uh, the iron in framed into hem that altogether have much higher affinity for electrons than cytochrome C, have higher reduction potentials, thus again generating the electromotive force. And these two iron sulfur centers in the heart of complex 4 finally donate the electrons taken from cytochrome C to the final acceptor, atmospheric oxygen, that picks these electrons and the protons from the negative side to get reduced to water, and this is accompanied by transfer of 2 protons on the positive side. So and this completes the cycle of respiratory chain pumping function, where altogether electrons are starting from complex 1 and 2 from NADH, and the succinate end up on oxygen with the highest reduction potential. And this is something, this difference generates electromotive force transfer to the pumping of protons. So if we carefully look at the outcome of each stage of proton pumping and add these equations together, we get a final balance equation of proton pumping between negative and positive side, where if we start from pumping transferring electrons from complex 1 and NADH, we transfer more protons from negative side to positive side than from complex when we start from complex 2, because again, unlike from complex 2, the electrons entering the chain from unlike from complex 1, so electrons entering the chain from complex 2 do not are not able to provide enough free energy of transfer to pump any protons, and that's why we have less protons pumped when transitioning from complex 1 to 4 than from complex 2 to 4.